so thanks for the introduction. I'm going to talk to you today about robust estimation, and we'll go deeper into what we mean by robust, because people tend to use different definitions around that particular adjective. And so we're going to apply the proposed estimation method to Gaussian processes, which we all know and love, and beyond for more general regression models. And this is joint work with my great collaborators, Ayush Harti, Jeremiah Snoblau, and FX Priol. Cool. So Bayesian inference was originally motivated in the context of experimental science, where there was a lot of domain expertise, and people tend to develop bespoke models, crafted likelihoods, priors that are very much specific to the problem, and kind of also relied on small and well-curated data sets. And that's, of course, not what we're dealing with in modern machine learning, where the problems are increasingly complex and poorly understood, and we even refer to them as black box problems. And as a result, our models become these kind of general flexible type that we would just hopefully be able to apply to any type of problems. And to make things worse, more complicated, the data sets are ever growing in size, complexity, and dimensionality. And under this shift in the scenario in which Bayesian inference is applied, model misspecification becomes more of a problem. And by model misspecification, I mean this scenario right here, where let's say I'm fitting a family of models p theta for some family of parameters theta, and my true data generation distribution is over here. There is no theta 0, the true theta 0, for which q is equal to p theta 0, which is, of course, what we would expect. And under this misspecification scenario, uncertainty quantification becomes brittle, and especially so in non-parametric models like Gaussian processes. Right, so here is an example of this happening, and specifically an example of the impact of having a couple of outliers on uncertainty quantification. So this is data of levels of the Nile River from year 740 to 860, roughly. And over that period, there were three extreme events, 3 years when the Nile flooded. And to demonstrate what happens when we feed a standard GP with additive Gaussian noise to the data set, we removed a few data points here in the middle and the end. And we'll see what estimated amplitude parameter of the kernel looks like. Yeah, so as you see, the uncertainty around the unknown region balloons inside, I would say unreasonably, because of these three surprising data points. The way we can think about it kind of roughly is that because these things happen, the likelihood principle tells us that, oh, there must be a lot of information in this region. So I'm really not sure what happens here, even despite it being close to data points who are pretty contained in this region. And in generative modeling, robust distance-based methods have been a practical remedy to this situation, but distances proposed between conditional distributions have not been tractable and really practical to work with. And that's what we propose. We propose a distance between conditional distributions that is to some extent plug and play, that only relies on a relatively small number of samples from two conditional distributions to fit. And as you see under this distance, EMCMD, or rather under parameter estimation with this distance, we have a better, kind of more reasonably behaved uncertainty quantification. Right. So to start with, if we want to compare two conditional distributions, one might observe that this is a challenging problem because it's effectively an infinite family of distribution against another infinite family of distributions. And one approach to doing this is mapping, sorry, before I go on, by X, I'm going to denote the space in which the points that I'm conditional live, and Y, the output space. So here in the illustration, I'm going to plot densities, but we don't require that densities exist for these distributions. So a thing that one might do is map every conditional into a space of functions that has some nice, well-understood properties that would allow us to compare two conditional distributions. And that is done by the means of something called conditional kernel mean embedding that maps every conditional distribution onto a function in an RKHS space of some kernel of choice, ky. So just to introduce a little bit of formalism, we'll refer to px comma something as a conditional distribution. I mean, it's a measure on y, and define the conditional kernel mean embedding of such distribution as a function of x and y. That's this integral over the chosen kernel ky, and integrate over the measure px dy. So now we're ready to introduce EMCMD as the distance between conditional distributions that makes use of these conditional kernel mean embeddings. So suppose I have conditional distribution P and Q, and these are the conditional kernel mean embeddings. As we said, they are defined on kind of a product of spaces X and Y. We consider the difference between them, and then take the norm in the RKHS HY to get a measure of, I'm going to say for now, measure of difference between P and Q at any point xi. So hopefully the interpretation of this should be for this point x. This purple line has a high value, so P and Q are very different at this point x, while around here they're very, very similar. And to summarize this difference over the space x, we take an integral over some measure nu, where we treat nu as a weighting measure. If nothing is known about the space x, it's sensible to and if x is bounded, it's sensible to take it to be a uniform measure, which would be equivalent to saying P being equal to Q is equally imported across all of the space x. If we have some knowledge around the problem of like regions that are more important, for instance, if we're dealing with quadrature over some known measure, we can use that measure as nu, or nu can be approximated through samples if we have some samples from a distribution that we know represents the importance of regions in X. And so we're going to investigate, of course, using this distance for parameter estimation. Suppose we have a family of models p theta for theta in some parameter space, and the true data generating distribution Q. Just for notational convenience, from now on, I'm going to say that mu theta is mu p theta. And we're going to target the parameter theta star that minimizes the distance between the embedding of p theta and the embedding of Q. And in a second, we're going to talk about why that's a good idea and what good qualities theta star has. But before that, if Q is a true data generating distribution, of course, we won't have access to it in closed form, and computing that integral that defines mu Q is not going to be really feasible. So in the real world scenario, we would have maybe n samples from Q, where possibly for each xi would only have one yi. And the measure nu, unless we choose it to be something analytic, might also only be available through a couple of samples from nu. So we don't have access to a bunch of these things. So we resort to a couple of approximations. We'll approximate the conditional kernel mean embedding through a solution to a certain vector-valued kernel-rich regression problem that has some nice proven optimality properties. And if you'd like to know more about that, I can go deeper into the detail later. But for the purpose of this talk, we can just trust me on the fact that this is a good choice of mu q hat. And we'll approximate the weighting measure nu just as this empirical V statistic. And so now we have a kind of a reachable estimator for theta as a minimizer of this approximated EMCMD with approximated weight measure and an approximated conditional kernel mean embedding. So now we're going to look at what effect does swapping theta star for theta hat, the approximation has. Will, at the limit of n and l going to infinity, will theta hat and l approach theta star? Before I go into theory, are there any questions so far? Yes?
Just from the, say, intuitive understanding point, from what I understood very well, so the problem is that we have some outliers that we should tend to overfit because of our kernel choice or because of the mean square error loss. Or could you rephrase intuitively? Because on the plot, to me, on first glance, it looked like, okay, it would take a smoother kernel maybe, or it would look already better.
So the best intuition I would give is if you look at the form of maximum likelihood of the loss function induced by maximum likelihood, it's this sum over log terms. So if something under the log is very close to 0, then it balloons, basically. So so it's a combination of the log kind of inflating our errors and the averaging being non-robust. So you know that effect where you'd have, let's say this is the data set and there is one outlier, the mean would be unreasonably shifted towards the outlier. So it's kind of a consequence of that. It's not specific to the kernel. Is that? Yeah. Yeah. Yes? Do you want me to go to a different slide?
Just for me that I see it again, the distance, the definition.
Oh, the definition of distance. Yeah. Okay. Cool. Let me check the time. Okay, so let's see what happens when we replace the true objective with an estimated one, and well, the true optimal theta star with an estimated theta hat n comma l. So there's a couple of properties that we would like this approximated estimator to have. First one is consistency, and this is a little illustration on what consistency means effectively. So let's say this purple line is the value of the true objective over different thetas, and it's minimized at theta star. And when I'm taking an approximation for different values of L and N, I'm kind of shifting away from the objective. So we say the objective is consistent if as L and N go to infinity at for each fixed theta, the dotted lines go to the straight line. If that convergence is uniform and under some assumptions on the space theta, we can even, and some assumptions on the minimizers that aren't out of the ordinary, that will give us consistency of the minimizer as well, which means that theta hat would go to theta star as well. So as n and L grow to infinity, we're going to have our estimated minimizers going to the true one. And we have that under some pretty mild assumptions. So I'm skipping the assumptions for the purpose of the talk. If you want to know about them, find me later. Yes, so we have the consistency, and moreover, we have that convergence that's not only uniform, but also exponentially fast, which is nice because exponentially fast convergence in probability under certain assumptions implies almost sure convergence, which is a pretty strong property. And on top of that, we can prove generalization, which is that the distance in the sense of true distance of EMCMD between any mu-q or any embedding of a distribution Q and embedding estimated with approximated EMCMD converges to the true EMCMD distance with between the true value, the value estimated with true EMCMD and mu-q. And that also happens exponentially fast. So one consequence of this generalization bound is that if the model is well specified, which means the true data generating process Q lies in this family, in this region for which we're looking for the true value of, for which we are, in which we're looking for the best approximating model, then the EMCMD between this true value of theta 0 and the approximation goes to 0 in probability and exponentially fast, which means that as n and L grow, we will reach, the distance between our solution and the true one will go to 0. But of course, what we're really interested in is a more realistic scenario of, let's say, Q is not in this family, or rather it's kind of almost there. It's not too far, it's kind of some distance away. Can we say under that assumptions that that this distance goes to almost 0? And we can formalize this through this construct proposed by Huber in the 1960s called epsilon Huber contamination, under which we assume that while Q is not equal to p theta 0 for any theta 0, it is a sum of p theta 0 times some 1 minus epsilon for a hopefully small epsilon, plus epsilon times some contaminating distribution. What that would mean for samples from Q is that in expectation, 1 minus epsilon proportion of the samples will come from p theta 0, so we'll be in a well-specified case, and epsilon will come from R, the contaminant distribution. So this is our quantification of the word almost. What if Q is almost p theta 0? And we see that under that, if Q is an epsilon contaminated distribution, then the distance between the true embedding, the true uncontaminated embedding and the estimated one goes to C0 epsilon exponentially fast. And while naturally we can't guarantee that it will go to 0, but if epsilon is close to 0, we kind of bound the error here. And C0 will only depend on the definition of the problem, so it doesn't depend on N or L. So that's a brief coverage of the theoretical properties. Are there any questions? Yes.
So if you say that C0 only depends on the problem, does that also mean it depends on the contaminant distribution, or is that?
It doesn't depend on the contaminant distribution, no. Give me 1 second, I answered very quickly. Let me think about that for 1 second. No, it doesn't depend on the contaminant distribution. Yes?
Question. So to me it seems like very related to variation.
So in variational inference, you would approximate an unknown distribution generally with something well understood, like a Gaussian. Here it's, I'm going to go back to the approximation to mu q hat. So the space in which this approximation lives will, in the general case, be smaller than the space in which the true kernel mean embedding lives. And there are some results that kind of bound convergence error based on the difference between these two spaces. But we can, unlike with variational inference, and please correct me if I'm wrong, we can guarantee consistency going into infinity. Well, with variational inference, there is nothing really saying that if we get an infinite number of points, we will converge to the true distribution. Okay, let me just. Right, so I'm going to go over some experiments that show how applying EMCMD to the problem of estimating the amplitude parameter of the kernel performs against maximum likelihood and some other commonly used estimators. So it's basically the setting is going to be similar to the motivational one of the Nile River, but a more of an expensive study. So just to reiterate, the setting here is that p theta is a marginal of a Gaussian process with 0 mean and some kernel c with amplitude theta. So c theta is theta times some fixed kernel. And the reason that we study the amplitude parameter is it has a great effect on the quality of uncertainty quantification of the model. This is a toy example where is the two identical Gaussian processes except for the value of the amplitude parameter conditioned on the same point, and the amplitude going from 0.1 to 1 kind of inflates these confidence regions greatly. So that's the reason that we care about the amplitude parameter being well estimated. So the first study I want to show you is kind of a toy well-controlled examples where we know that the true function is a sample from the Gaussian process. 95% of data have Gaussian noise, additive Gaussian noise. 5% have added student T noise. And the modeler assumes the noise is Gaussian, as this is the easier, it's an easier model to work with. And this is just an example of what the setting would look like. So here in black, F is a sample from a GP. Blue points have added Gaussian noise, and these two red points are outliers. I think it's 2% of outliers, looks like 2% of outliers have student T noise. I should also probably say that this picture is for visualization purposes because we picked kind of zero-centered student T noise. Most outliers aren't kind of that far away from the blue point and aren't that obviously visible from the picture. And this is the result of estimating the amplitude for this misspecified setting where we have 5%, where we have 5% of outliers, and we compare the performance of EMCMD, leave one out cross-validation, which has a closed form for the case of GPA regression, and maximum likelihood. And we see that as the scale of contamination grows, as the scale of the student T noise, scale of the student T noise increases in comparison to the scale of the Gaussian noise, maximum likelihood shifts more and more into overestimating the amplitude and being more underconfident, which is the effect that we saw with the Nile dataset. Same with cross-validation, but EMCMD kind of stays more or less centered around the true value of the amplitude. And as a result, this supports our claim that maximum likelihood, and Leavenworth cross-validation kind of for the same reason, are not in general robust to outliers, and EMCMD displays robustness here. So the second more real-world experiment that I want to show you is fitting a wind farm model, or building an emulator of a wind farm simulation model that has 5 inputs that are, I think, directions of wind and some other parameters, and the output is the amount of energy produced. And here we compare the calibration of posterior GPs where the amplitude parameter was fit with maximum likelihood versus EMCMD kind of more explicitly, where here we plot the relation to the real proportion of data that falls into some region around the mean to the proportion of data that should fall into that region as far as the model is concerned. So this, a perfectly calibrated model would be exactly y given x. So sort of the model said 60% and the reality is 60%. Being above the curve is underconfidence. The model said only 60%, but in reality it's 80%. And under the curve is overconfidence. Again, we see the same scenario that we observed in the previous experiment and in the Nile one, that maximum likelihood is underconfident over 100 runs of the experiment, I think. And EMCMD is pretty close to good calibration, tiny bit underconfident here. And this is just telling the same story where we are using some metrics on these calibration diagrams to show the difference between them. This is both of them consider, no, sorry, I think the expected, yeah. This is considering the volume of the region under the curve, and this is the maximum difference. So the smaller the better, and yeah, see, EMCMD generally has smaller error than the maximum likelihood. Oh, so the last one is close to heart to some things that we've been talking about. We wanted to consider the case of Bayesian optimization and specifically what happens if an outlier doesn't affect the location of the maximum. Let's say we're maximizing this function, but it will, of course, affect how we are modeling the function. So in this toy example, the star is an outlier, it's somewhere down the bottom, and there's 2 maximum that are on these peaks over here. Maximum likelihood overinflates the size of confidence intervals, as we saw multiple times by now. So even though the outlier does not affect the location of the maximum, for a set of acquisition functions, we are now more likely to look in this unpromising region, really, just because the confidence of the model there is so low, it wants to go and explore over here. So this is the kind of scenario that we would like to avoid and want to see if it can be avoided by using EMCMD instead of maximum likelihood. Yeah, and this is in this example, yeah, EMCMD less underconfident, and the acquisition functions are more likely to go and explore in more promising regions. So this is a more, well, in a certain sense, a more real setting. This is a running Bayesian optimization on a Hartman 6D function that's very kind of peaky. And we are adding outliers that are kind of truncated at the top, so they don't change the maximum. And we see that EMCMD reaches the maximum faster than, reaches the maximum of the function faster than maximum likelihood here. So cumulative regret is lower. Even in the case where we had no outliers, but that's because originally the problem is fairly misspecified. So yeah. So that's it for this work. Oh, before I do this, are there any questions on the experiments? Yeah.
Can you go back to the slide where you showed the robustness originally?
Of what?
First results.
The first one, this one.
Yes, this one. So it looks like the EMCMD estimator is like spreads a fair bit more than the other estimators in all scenarios, even though it's
I mean, this is log scale, so I wouldn't say that it spreads. Like the distance between this and this is way smaller.
Yeah, okay,
yeah.
But I mean, there's still an effect there, right? So
there's an effect that it underestimates. So I should double check this, so I'm not going to state it too confidently. But because these outliers are still zero-centered, I would guess that at least some of these cases are well specified. And in a well specified case, of course, maximum likelihood is great. That's the perfect solution. If your model is well specified, go use maximum likelihood. And in the well specified case, yes, EMCMD is definitely worse than maximum likelihood.
So to double check, you would expect the spread to be sort of amplified with ML in the case where there would be colored or non-zero mean noise in the contaminant distribution here?
Just in cases where these two outliers, kind of the farther they go from looking like Gaussian additive noise, the closer, the farther they go from being from looking like they were sampled from Gaussian additive noise, the worse a maximum likelihood would become. Yes?
For the last numerical experiment you showed, it looked a bit like if you have outliers, then the two solutions are a bit closer together. So the advantage of EMCMD seems to be more pronounced if there are no outliers.
So frankly speaking, I think it's an artifact of the problem. Here, unlike in the very controlled GP regression case, so here the setting is we're very cleanly in the epsilon contamination case. 1 minus epsilon data came from some well-specified setting, and epsilon came from some contamination. While in here, the no outliers case is by no means well-specified. So it's already a misspecified problem, because Harman 6D function doesn't look like a sample from a Gaussian process, or at least not. Yeah, no, maybe not one with the Matron kernel that we used.
Is this ratio of contamination something that goes into the EMCMD method?
Is this ratio of contamination something that goes into the? So in the robustness result, we do assume that epsilon is known, and yeah, this convergence to epsilon is, yeah, this is where it comes in. But again, this result, it assumed that the p theta 0 is known to come from the p theta family, right? Which which is not the case for this Bayesian optimization problem. So in some sense, this goes beyond the setting that we considered in theory, and we kind of show that it still works. Yes?
So could the experimental effect here be, loosely speaking, the noise actually makes the Hartman function look more like a sample from a Matron Gaussian process?
I mean, that's what it feels like, but I don't want to be too confident about it. But yeah. It's hard to visualize a 6D function, but yeah. Yeah, when I looked at the projections, they didn't really tell me anything. But yes?
I have one question. First, I have to promise I have zero knowledge in probabilistic program numerical methods. So
Okay.
my question is, okay, this EMCMD measures distance to find some distribution function, right? So maximum likelihood uses the same distance, or how do you define parameters?
Oh, that is actually a great question. Maximum likelihood.
Waiting for that one. And here it said, okay, this variational inference actually uses this between two distributions. So have you thought of not maximum likelihood, but this scale divergence?
Maximum likelihood optimizes scale divergence. That was a great question. And yeah, KL divergence has the same log sum situation happening. I mean, yeah, they are, the minimum is the same.
So, okay, sorry. But KL divergence is still, if you take posterior, it's very hard to compute, right? Or it's not. You just only compute likelihood part, or you compute posterior?
So where we take the posterior here, we use the same Gaussian likelihood that was original. So we don't change the character of inference. We change how the empirical base step is done, or how the parameter of the kernel is selected, and then inference is done the usual way. So there is no variational inference happening. It's normal GPU conditioning.
Can you back to the slide where you showed kind of what looked like a GP posterior, but instead of having the observations y, you have the kernel function ky? It's like none of the experiments was before.
Not in experiments, but look like a GP posterior. I'm not sure which one you're referring to. This one, okay.
So for mu hat q, like this looks like a GP posterior mean function, right?
It is, yeah. It's a result of doing kernel regression in this vector valued setting, which is of course the same as, yeah.
So I guess my question is, can I think of this approach as something like, I'm doing something to my observations, which is defined through this kernel ky, to somehow modify the observations, and then I do regular GP regression on that? Or is that?
You can think of this approximation to the conditional kernel mean embedding as you're putting a certain prior on the true value of the conditional kernel mean embedding. You're assuming some additive noise, and you're taking these ky's of yi as noisy observations of the true conditional kernel mean embedding, but that doesn't propagate that cleanly to the expression of the expected EMCMD. If I were to write it out, it would be like sum of square root of. So it's not an M estimator, and it's yeah. I think the answer to your original question is at least not directly, or I don't know how to do that. But yeah, this bit can be seen as doing a GPU regression on the CKME.
Just looking at this expression, this almost gives you an intuition of something like, okay, there's some smoothing of the observations going on.
Yeah. So that is a very useful intuition of this. It's like I want to know what my function, because this conditional kernel mean embedding is a function, right? What is going to look like at some xi that I haven't observed, and I am assuming some correlation structure between these different guys, and doing a weighted sum between them, and and from them getting the value of this guy. Yeah. Cool. Okay, so I'll run through the 3 minutes. Okay, so let's just go over the conclusions and future work, and I want to pitch some extra little bit of work that we did at the end. Right, so conclusions for this bit is we introduced a notion of distance between conditional distributions. We showed how to approximate it and run a parameter estimation with the approximated distance, and showed that it's optimal in the sense of consistency, generalization, and robustness. And a thing that I wanted to point out is, so far you might have noticed that I'm assuming that I can get mu theta in closed form, which is the case for GPs and certain choices of KY, Matron and RBF. But that, of course, will not be the case for general models P theta. But it turns out that if I approximate both this embedding as well as the mu q, the optimality results still hold with a little bit of extra assumption on top. So in that sense, the estimator is general purpose. And yes, someone mentioned inference. We would very much like to apply this to the inference step as well, and try see if it can robustify generalized Bayesian inference. And finally, very loosely related to the talk, I just wanted to pitch some recent work that we've done. This one is out on archive. So here we, again, look at MMD in a slightly different context. Here the setting is likelihood-free inference, where my model is something black box, let's say the output of some simulator, and to optimize it, because I don't have an expression for the likelihood, all I can do is sample from the model by feeding it samples from some known distributions, fat U, and running the simulator over these UIs, and that's how I get the samples from P theta. And then a common way to optimize theta is to minimize a notion of distance, MMD being the common distance. I know that I haven't gone into what MMD is, but it's also in a similar sense distance between embeddings of distributions. So minimize the distance between empirical distributions that I get from samples, where Q hat is the samples. Is gotten from samples that I got by definition of the problem. That's the true data, and P hat n is an approximation of the true P theta using the samples that I go through this running through simulator procedure. And approximating MMD in this setting involves approximating this integral, which has through a very direct connection to Bayesian quadrature. We can show that in a certain setting, under certain assumptions about the newly introduced kernel C, we can show that this set of weights is optimal for the approximation, and this method with this new optimal set of weights has a significantly improved sample complexity from the naive statistic estimator and the previous state of the art, which is QMC. And if this is something that you're interested in, go check out the paper and our results on it. That's it.